Hi, welcome to the video solution for Edexcel IAL Physics. This is a new specification paper 3, WPH 13 Unit 3 for June 2019. So let's start. Question number 1. During experiment, a student used a measuring instrument shown in the photograph to measure the diameter of a small metal sphere. This is an instrument, metal sphere. State the resolution of measuring instrument shown in the photograph. So in this instrument, you see we have digital meter. So idea of noting down or idea of to check the resolution is the decimal place. If you see the decimal place and number of digit after decimal place, how many digit do you have at the right side, and then you can make the rightmost digit as 1, and then you can decide the resolution. So suppose if you have a 2 decimal place, this is decimal, and you have a 2 digit, that means you can make the first one as 0 and the last one as 1. So you can say that the resolution is 0.01. But in this case, you see the decimal is here. That means the resolution will be 0.1 millimeter, because you have a 1 decimal place after the this decimal. So you can make it just 1. So this is the resolution. Second part, explain why this device is suitable to measure the diameter of the metal sphere. Clearly, again a typical question, you compare resolution of the instrument with the size of the object. So diameter of this metal sphere is much greater than the resolution. So that means if diameter is larger than the resolution, so you have a small uncertainty or more accurate value. So this instrument is suitable. Part B, the student measured the diameter. The reading obtained was 20.5 plus minus 0.05 millimeter. Calculate the percentage uncertainty in the measurement of the diameter. If you are given some measurement along with uncertainty, so percentage uncertainty is uncertainty divided by the measurement multiplied by 100. That's how you find the percentage uncertainty. So in this example, you say 0.05 millimeter divided by 20.5 times 100, and it will give you your uncertainty 0.24%. This is percentage uncertainty in the measurement of the diameter of the sphere. The student took further measurement of the diameter and calculated a mean. Describe how the student should use the measuring device to make the measurement as accurate as possible. Again, a typical question, using a device to get as accurate as possible. We say that the student is going to use the given device, and he or she will take the measurement from different orientation and then use the mean value to get the accurate value. And moreover, you can include the check the zero error before starting your measurement. So that's how you can incorporate all the comments. So check the zero error and then take the measurement at a different orientation, and so she is taking already taking mean value here, so you don't need to write in this answer. The student measured the diameter of a second metal sphere and recorded the following reading. So these are the multiple reading of a second metal. Calculate the mean diameter of the metal sphere. Generally in these types of questions, when they give you set of reading for one type of measurement, generally they want to check your concept of anomalous reading, whether you know that there might be anomalous reading, so you just get rid of this reading in your calculation. So this is 19.0, 19.1, 18.9, 18.3 and 19.1. so this 18.3 is quite away from your rest of the set of the value, so you just discard this value. This is your anomalous reading. I'm just cutting to show you. You don't need to cross this number, but you don't include this reading in your calculation in every step. So if you need to find the mean, so mean is 19.0 plus 19.1 plus 18.9 plus 19.1 again, and divided by 4. Remember, not 5. We have 5 readings, 1, 2, 3, 4, 5, but we have discarded this value. So you can find the mean value from this equation, and the mean value will be 19.025 if you use your calculator, which is 19.03. but our every measurement in one decimal place, so we round it off this mean value as 19.0 millimeter. This is our mean value till one decimal place. Calculate the percentage uncertainty in the mean diameter of the second metal sphere. I told you that percentage uncertainty is uncertainty divided by measured value, or measured reading. So your measured value is 19, but you don't have uncertainty to find the percentage uncertainty. So first we figure out what uncertainty we have in our calculations before finding the percentage uncertainty, and there will be 100 here, of course, but before finding percentage uncertainty we need uncertainty, and uncertainty in the reading is range divided by 2. So you find the range of the set of value and divided by 2 will give you uncertainty. That means you can say that you have a maximum value of your set of reading, or maximum reading is 19.1 minus minimum reading is 18.9. So 18.9 divided by 2, it will give you, I'm just writing in short, uncertainty. Okay, fine. Uncertainty is 19.1, 18.9, which is 0.2, and 0.2 divided by 2, it will give you 0.1 millimeter, and this is your uncertainty. So your percentage uncertainty will be 0.1 multiplied by divided by measured value, which is 19.0 times 100. That means it will give you 0.5, so 0.00528. So 0.00528, 0.0053 multiply by 100. Of course, if you divide these and multiply by 100 will give you 0.53%. So this is your percentage uncertainty. The student measured the mass of the first metal sphere using a top pan balance. The mass reading obtained was 35.6. Calculate the density of the first metal sphere. So you know that they are talking about first metal sphere, and we need to find the density, and density is Density is mass over volume. We have mass gram, so we convert this into kilogram. That means 0.0356 kg, and we need volume. For volume, we are going to use formula for V is equal to 4/3 of pi r cube. So we have diameter of the sphere, and diameter d1 of the first sphere, diameter is 20.5 plus minus 0.05. So this is the measured diameter. So you can use this diameter here. You can divide it by 2, or you just say that V is equal to 4/3 of pi r cube. R is diameter divided by 2. So you can say that this is 20.5 10 to the power minus 3 and divided by 2. This is your radius. Remember, this diameter is in millimeter, and we are doing calculation in SI system, so you need to convert this millimeter. Is better to convert millimeter in meter in the first step. Otherwise, when you take more power like cube, so sometimes students gets confused. So it's 20.5 times power minus 3. Now it is in meter divided by 2. It is radius whole cube. So if you do your calculation, so you will find V1 would be equal to 4.5 into 10 to the power minus 6 meter cube. And then density D would be equal to mass over volume, and mass is 0.0356 divided by volume, 4.5 into 10 to the power minus 6. And finally your diameter will be 7896.05. That means diameter, finally you can say that sorry, it's not a diameter. I'm sorry, I'm saying again a diameter. It's not a diameter. This is density. I'm sorry about that. This is density that we are finding. Okay, so density of the metal sphere D is 7.89 or 7.9 if you wish, or 7.89 into 10 to the power 3, or 7.89 into 10 to the power, because we are shifting right left side, 10 to the power 3 kilogram meter minus 3. So this is the density of the metal sphere. Next, the student calculated the density of the second metal sphere to be 7.75 10 to the power 3 kg meter minus 3 within an uncertainty of 2%. Within an uncertainty of 2%. So determine whether the two sphere could be made from the same metal or not. So you are given uncertainty of 2%. That means your uncertainty in the measurement is 0.2. So the idea behind this calculation is, first we are going to find the uncertainty in the density, because this is given your 2%. So first we are going to figure out uncertainty in the density, and then using this uncertainty we will going to find maximum and minimum density of this second metal sphere. So we will have D2 max and D2 min, meaning minimum. So minimum density and the maximum density with respect to the given range of uncertainty, and then we compare whether our calculated density of the first sphere is lying between these range. If this density lies between the range of densities maximum minimum of the second one, so we can say that yes, indeed there's a chance that the first metal is made of the same metal. So first we need to figure out how much uncertainty is there for the second metal if uncertainty 2% is there. So we multiply. So I'm just giving symbol for delta D2. This is uncertainty in the density of second metal sphere, which is you can find by multiplying 0.02 2% of 7.75 into 10 to the power 3. And if you do that calculation, so you will have answer of uncertainty delta D2 would be 0.155 10 to the power minus 3, 0.155 10 to the power 3. Yeah, this is 3. Or you can round it off 0.16 into 10 to the power 3 kg meter minus 3 if you wish. Kg meter minus A, because this is uncertainty. Now you have uncertainty, so you can find maximum density and the minimum density. So maximum density is, so D2 max will be measured value plus your uncertainty. So you can say that 7.75 plus 0.16. So you have a number, maximum density will be 7.91 into 10 to the power 3. You just write the unit here. And then minimum density, D2 minimum density. So minimum density is measured value minus uncertainty. So 7.75 minus 0.16. So you have 7.59. 7.59 indeed 10 to the power 3 kg meter minus 3. And now, since the density of first metal 7.89, if you see 7.89 is the density, I'm not including 10 to the power 3 is there, so 7.89 lies between 7.59 and 7.9. That means it is possible that the first metal sphere is made of as the same material as that of the second. That's what you need to write. There's a statement. Okay, I don't have a place, so you must write that the 7.89 is greater than 7.59, less than 7.91. So of course it is made of same metal. Question number 2. A student investigated the extension of a spring to determine its stiffness. The student suspended the spring from a fixed support and added mass to the lower end of the spring as shown. Okay, this is the arrangement: spring, mass, fixed support. The student used a meter rule to make measurement of the spring as the mass was increased. The student plotted a graph of applied force F against the extension of the spring X. Fx graph. Describe what the student should do to obtain the data to plot the force extension graph. So you need to basically write the plan or describe the plan to take the measurement from this reading. So you can say that first of all, a student should use the original length. So the unextended or unstretched length or original length L naught, and then um, he must, or he or she or the student should keep adding the various weight and noting down the final length L dash, and then subtractive difference between these two lengths will give the extension from which and then extension. After that, the force acting on the spring is in fact weight of the hanging mass that can be found using m into g. Moreover, the gradient of the yes f is equal w into m into g, because you need to write the plan only. And of course you need to say about the measuring technique, that the student make sure that the ruler to measure the length should be vertical, so he can use or she can use set square to measure the to make ruler perpendicular. So you can include all these points. Explain how you would use the graph to determine the stiffness of the spring. Of course, stiffness from force extension graph is the gradient of the linear region. If you go back, you see you have a graph, force extension graph, a straight line, but you have a curve later on after some particular value of f. So you need to calculate the gradient of this linear region, which gives you stiffness of the spring. Question number 3. A student used an electron beam tube to accelerate electron towards a thin slice of graphite. As shown, the electrons passing through the graphite produce a diffraction pattern on the screen. This is similar to the effect seen when the light passes through a diffraction grating. This is the diffraction pattern, typical electron diffraction pattern that comes in exam. So the diffraction pattern seen on the curved screen is shown below. Remember, this pattern is seen here. This is, you can imagine, this is the bulb. So this is the curved surface. You see the pattern, this diffraction pattern. Describe how the student can accurately determine the radius of the first bright ring of the diffraction pattern. So now you can refer this diagram, and you can say that a student can use because the screen is curved, so a student cannot use meter rule, because the screen is curved. So a student should use either a flexible measuring tape so that it can bend, or maybe the best option is the student should use a vernier caliper to measure the distance between two positions, and he must take the at least two readings, so that he can use the average in order to get accurate result. And of course, dividing by 2, he or she will again have the radius of this ring. And if in order to improve the accuracy, the student should try to put or to measure from middle of the bright region of the ring, so that a student can get as accurate as possible the diameter of the ring. So that's how you can incorporate all the comments. So the surface of the bulb is curved, so accurate radius cannot be found, but vernier caliper can be used to find the diameter. The student should take at least 2 reading. Dividing by 2, it will give the diameter, but a student should try to take the measurement from the middle bright region of the ring. Explain how diffraction pattern provides evidence for the wave nature of electron. Again, a typical question from this topic. You can say that when electron pass through the crystal, the graphite, whatever they give in the question, when electron beam pass through these slice or graphite, they diffract, and after diffraction they interfere with each other, and after interference they produce interference pattern, diffraction pattern, and which is the wave behavior. So electron is behaving as a wave. Part C, the student determine the radius of the first bright ring of the diffraction pattern for a range of electron energies. The student then calculated the de Broglie wavelength lambda of the electron and the angle of diffraction theta. The results are shown in the table. These are the various values of the wavelength and theta. Criticize these results. Again, a typical question of unit 3, criticizing the result. Most common answer: less number of reading, inconsistent significant figures. You can see here we are using 3SF, we are using 2SF, again 3SF. So we have inconsistent significant figure, less number of reading, and of course a small range are there from 1.9 to 3, or from 10 to only 19 degrees, just 9 degree difference is there. So a small range the student is using, and moreover no repeat reading is shown in any column. So that's kind of stuff you can write, and these are the most common or typical answer for this type of question. Use the result in the table to plot a graph lambda on the y-axis against sine theta on the x-axis. On the grid provided, use right-hand column for of the table for your process data. So now you have this table, and this is the incomplete one. So you need to find sine of theta. So you calculate sine of 19.2, sine of 17.2. I guess all these stuff. So when you calculate sine of all these, so you have these values. So once you have these values, so you need to plot graph between lambda on y-axis and sine theta on the x-axis on the graph. So here we have a graph, and this is the values that we have, and we need to plot lambda on the y-axis, sine theta on the x-axis. And if you see, you need to be careful about selecting the scale on the plot, because you have very small values, decimal values. So it's a matter of practice. How much do you do? So that's how you can see. On the x-axis we have sine theta value starting from 0.189 reaching 3.329. So we have I started 0.18, 0.32. You can choose, because this is a small graph. So this is my x-axis, and on y-axis this is lambda 10 to the power minus 11 meter. So starting from 1.8, 2, and so on. And now you can plot all the graph. So if you plot all the graphs, 5 points at 0.189, you have 1.9, and these points, if you plot, then you can have these 5 points. And then after plotting this, you need to plot a line of best fit, the line that are either passing through all the points, or all the points are equally distributed from the line. So but this is quite easy. If you plot the line of best fit, so this is some kind of a line of best fit, and you can see that this point is slightly above and this point is slightly below. Rest of the pointers are approximately on the line. So this is almost your line of best fit. Determine the gradient of the graph. So here is your graph, and then how do you find the gradient? Remember, in order to find the gradient, you need to choose two different points, different than the plotted ones, and try to choose 2 points so that you can draw a big triangle. So I am choosing 2 points on the line. If you see these 2 points, I am choosing that point here and this point, and these are the coordinates of the point. And now if you need to find the gradient, so gradient is y2 minus y1 over x2 minus x1. That means you can say that 3.38 minus 1.8, and we have 10 to the power minus 11 divided by x2 minus x1, and x2 minus x1 will be 0.32 minus 0.18, and if you simplify this, you have answer 11.2 into 10 to the power minus 11. And what should be the unit? Because this is lambda over sine theta. Sine theta has no unit, so lambda has a unit meter. So this is meter, and this is your gradient. Or you can write gradient as 1.12 into 10 to the power minus 10 meter. This is the gradient. The diffraction occurs as electron pass through the thin slice of graphite. The atom in the graphite are arranged in layers. The position of the rings in the diffraction pattern can be approximated by the equation n lambda equal to d sine theta, where d is the spacing between the layers. Explain why spacing between the layer is given by the gradient of the graph. So if you rearrange this equation as d, meaning if you make d as a subject, so d can be written as d is equal to n lambda over sine theta, or d is equal to n into lambda over sine theta, which is gradient. And if n equal to 1, and why I'm taking n equal to 1? Because I'm considering the first order ring. So first order ring, if n equal to 1, so d is equal to gradient. And I'm sorry about my writing, it's not, of course, good. So this is gradient. Question number 4. A student carried out an experiment to determine the mass per unit length mu of a string using a standing wave. The standing wave produced is shown in the diagram. So this is the diagram, a typical diagram of a standing waves question. The student recorded the following data: length of the string L 1.25, frequency is this, mass is this, calculate mu given the equation below. So you need to find mu from this equation. So it's a quite easy question of 3 marks. You need to make mu as a subject. You just rearrange for mu. So you just remove the square root. So you say that mg upon mu would be equal to f square and lambda square. So mu would be equal to mg upon f square lambda square. And in this equation, m, we have value of m, g is 9.8, f square, and value of f is 105, but we don't have lambda. But if you see, this is the standing waves. So from the diagram, we know that we have 3 loops, and we have a relation between length L and the wavelength. So we can say that 3 loops mean this is 0.5 lambda. So you can say that we have 1.5 of lambda is equal to length. So lambda is equal to length upon 1.5, or lambda is equal to length is 1.25, so 1.25 divided by 1.5, and then lambda is 0.833333 meter, and you substitute all the values here. So mu would be equal to m is 0.25 times of 9.81 divided by f square 105 whole square times of 0.833 whole squared. So mu will be 0.00032 meter. No, it's a mass per unit length, so it is not meter, it is kilogram per meter. And if you wish, you can leave it here, or mu is equal to 3.2 into 10 to the power minus 4, yes, 1 2 3 4 minus 4 kg meter minus 3. This is your mu. Identify two significant sources of uncertainty in the student's measurement. Of course, two sources of uncertainty. One is measuring in length, because it's really difficult to measure the length. It is vibrating. It's really difficult to point out the position of node and anti-node. And the second source of uncertainty might be in the mass, because there might be a zero error in the mass balance, or maybe uncertainty in the frequency, because there might be a fluctuation. So in all the three, if you go back, in all the three you have uncertainty. There might be a parallax error in length, fluctuation, so that you cannot have exact position of node or maybe anti-node, and mass, there might be a zero error. So that's how you can write any of the two, because 2 marks, or you can include all the three. And for each of these sources of uncertainty, describe an experimental technique the student could have used to obtain accurate reading. Again, for measurement of length, in order to reduce parallax error, take multiple reading, use a set square so that the ruler stays perpendicular, or the string should be straight when you are doing your measurement. And for mass, you can say that the zero error should be removed before taking the mass. So that's how you can say. Thank you very much for this video. I hope you enjoyed it. Take care. Have a nice time.